Welcome to this explainer. Today, we're diving straight into Chapter 3, Current Electricity. We're going to break down the unseen, absolutely fascinating mechanics of the steady electricity that literally powers our everyday devices.
To kick things off, let's ask ourselves a kind of simple but profound question. Why is a chaotic lightning strike over in an absolute instant, while the flashlight in your hand provides a smooth, reliable, and continuous beam of energy? Right? Both involve the movement of electric charges, but the way those charges behave is vastly different. And today, we're going to unpack exactly why that is.
Okay, here's our roadmap. We'll be looking at the flow of charge, Ohm's law and resistance, the secret life of electrons, breaking Ohm's law, temperature and material resistivity, and finally, powering up, EMF and cells. Let's get right into it.
Section 1. The flow of charge, steady versus transient currents.
So when we talk about electric current, we're really talking about movement. Imagine a small cross-sectional area inside a wire. You've got both positive and negative charges that might be moving back and forth, but the current is the net amount of positive charge flowing in the forward direction across that area over a specific time interval. So the crucial takeaway here is that current is essentially a measure of traffic, specifically the net charge crossing a checkpoint over a given period, and we measure this traffic in amperes. Managing this traffic is exactly how we ultimately deliver electrical energy and power to all your devices. Now, what's really wild is the sheer scale of amperes in nature. It's staggering. Nature provides both ends of the extreme. An average lightning strike, which, by the way, is not a steady flow, but a massive, transient dump of charge, carries currents on the order of tens of thousands of amperes. On the complete opposite end of the spectrum, the electrical currents flowing through our own biological nerves are measured in tiny microamperes. And our household appliances, they sit comfortably right in the middle of these two extremes.
Moving on to Section 2, Ohm's law and resistance, the grand rule of the road. This brings us to a fundamental concept discovered by George Simon Ohm way back in 1828. On the macroscopic level, the stuff we can easily measure with a multimeter, voltage is directly proportional to current, which gives us the famous equation V equals I times R. But there's a microscopic equivalent happening inside the metal too. Down at that tiny scale, the current density, which we call J, is directly proportional to the electric field E driving it, and they're linked by the material's conductivity. So the macroscopic and the microscopic are perfectly intertwined.
But let's zero in on that R for a second. Resistance. Resistance isn't just some arbitrary number. It depends heavily on the physical shape of the conductor. It's directly proportional to length and inversely proportional to cross-sectional area. To put that into perspective, if you take a wire and double its length, you double the resistance because the electrons have to travel twice as far through the obstacle course. But if you cut its cross-sectional area in half, the resistance doubles as well because you've essentially narrowed the road. And all of this is tied together by ρ, a material's intrinsic resistivity.
Section 3. The secret life of electrons, a microscopic pinball game.
Now, you might picture electrons zooming straight through a wire like cars on a perfectly clear highway. Well, the reality is totally different. Inside a solid conductor, electrons are actually navigating a background of fixed, massive positive ions. When an electric field is applied, the electron accelerates, but almost immediately, bam, it collides with one of these massive ions. It loses its forward speed entirely. Then the electric field grabs it, accelerates it again, only for it to crash again. So electrons don't sprint to the speed of light. Instead, they play this chaotic game of pinball, constantly accelerating and crashing into fixed positive ions. And honestly, this perfectly explains the physical origin of resistance. Because of all this constant crashing, they only manage a very slow average forward progress. We call this steady average speed drift velocity. And how easily these electrons can achieve this drift through the atomic obstacle course is measured as their mobility. So even though an individual electron is accelerating and stopping constantly, if we average out the motion of all the electrons over time, using the average time between collisions, which is known as relaxation time, we find they move together at a steady, surprisingly slow pace. This completely overturns the whole myth that individual electrons zoom instantly from the power plant to your house.
So you might be wondering, how on earth does a slow drift create enough power to run your house? Well, look at this staggering number. The number density of free electrons in a standard conductor, like copper, is a massive 10 to the 29th power per cubic meter. The drift speed might be tiny, and the charge of a single electron is incredibly small. But when you have an absolutely enormous army of 10 to the 29th electrons moving together, that slow drift adds up to a very significant macroscopic current. Section 4. Breaking Ohm's law when the rules don't apply. Ohm's law is incredibly useful for sure, but it isn't a fundamental law of nature like gravity. In fact, many vital electronic components actually break these rules. For instance, sometimes voltage just ceases to be strictly proportional to current. In other devices, like diodes, the relationship depends entirely on the sign of the voltage, meaning it might conduct electricity perfectly in one direction, but block it completely if you reverse the voltage. In cases like these, the relationship between voltage and current becomes completely nonlinear. If we look at the data for a real conductor, notice the deviation in action. A perfectly straight linear dashed line is what Ohm's law predicts, a perfect continuous proportionality. But look at the solid line representing a real, good conductor. As the current increases, the line starts to curve away from that dashed prediction. The resistance is actually changing. It's no longer a straight, predictable line. This proves that Ohm's law is an excellent approximation for certain ranges, but definitely not an absolute rule. Section 5. Temperature and material resistivity. Changing the playing field. This categorizes our physical world beautifully based on electrical resistivity. Metals, our standard conductors, have incredibly low resistivity. Insulators like rubber and ceramic have resistivities up to 10 to the 18th power greater than metals. They practically block flow entirely. Semiconductors sit right in the middle. But look at the far right. This is the really fascinating part. When you apply heat, these materials react differently. Metals actually become worse conductors as they heat up, while semiconductors uniquely become better conductors as temperatures rise. It's a total game changer. Let's see how this builds on our pinball analogy from earlier. For metals, the temperature dependence of resistivity, specifically the temperature coefficient represented by the Greek letter alpha, is positive. Conceptually, this makes perfect sense. Remember those positive ions that the electrons keep crashing into? Well, when a metal heats up, those positive atoms vibrate wildly. This creates a much more chaotic, difficult pinball machine for our electrons to navigate. More vibration means more frequent collisions, a shorter relaxation time, and therefore higher resistance. Section 6. Powering up, EMF, and cells. We hear the term EMF, or electromotive force, a lot when talking about batteries. But the name is actually a bit of a historical trap. It's really important to clarify that electromotive force isn't a physical force at all. It's not measured in newtons. It's actually the work done per unit charge by a source to move that charge from a lower to a higher potential energy. Simply put, it's the maximum potential voltage difference between the positive and negative terminals of a battery when the circuit is open and absolutely zero current is flowing. But, of course, we don't live in an ideal world. In a perfectly ideal cell, the battery gives you its full EMF to run your devices. But in reality, the chemicals and the electrolyte inside the battery have their own small resistance to the flow of charge. We call this internal resistance, or lowercase r. Because of this internal resistance, a real cell basically steals a little bit of the voltage before it ever reaches your external circuit. So the actual voltage you get is the EMF minus the current times that internal resistance. And because single cells have these limitations, we often combine them in series to boost the total voltage, or we combine them in parallel to increase the available current for our circuits. Okay, before we wrap up, I want to share a highly unintuitive fact from the source material. When we draw circuits, we always draw current with a directional arrow. It feels like a vector, right? But it's made super clear here. Current is definitively a scalar quantity. It is simply a magnitude. When currents meet at a junction, they do not obey the complex geometric laws of vector addition. They just add together like simple numbers. So, we've mastered the fundamentals of a single, steady flow of charge today. We've seen how electrons drift, how resistance is born from collisions, and how cells drive the whole process. But the source material leaves us with a really provocative thought. What happens when the circuitry gets messy? How do we calculate the chaos when this river of electrons doesn't just flow in one loop, but splits into a complex, interwoven web? Well, that requires stepping beyond simple Ohm's law and diving into Kirchhoff's rules and applying them to clever configurations like the Wheatstone Bridge. How exactly do those rules balance the traffic of charge in a tangled grid? That is a puzzle to leave you thinking about until next time. Thanks so much for joining this explainer, and keep questioning the mechanics of the world around you.